Behind proof by contradiction. So, so the proof by contradiction is this idea that let's say I've got some statement P, and what I'm trying to do is I'm trying to show that P is actually true. I'm trying to show that P is actually true, and the way I'm going to proceed is by assuming, because I'm using proof by contradiction, I'm going to assume that let's assume that not of P not of P is actually true. Okay, so by assuming that the negation of P is actually true, I'm then going to perform some series of inferencing. I'm going to do some series of inferencing, and let's say as I do these inferencing, I'm going to come to some conclusion, or I'm going to state some fact after performing this inferencing that let's say R is true, and then I might do some more inferencing and then come to saying that not R is true here. The moment I get some kind of a contradiction, which says that look, R should be true and not R should be true. This is saying R and not R should be true. Well, you cannot have R and not R both being true at the same time. And because of this contradiction that resulted from an assumption that not P must actually be true, this contradiction tells you that not P must be false, meaning not P must be 0, which implies that P should be 1, meaning P should be true, which, going back to the original statement, P should actually be true. Now, this is kind of the general high-level idea, but if I were to do this a little bit more concretely, let's assume that I've got a statement where I've got some statement P, which is logically equivalent to saying if Q, then R. Okay, so whatever the statement P is that I'm trying to prove, I'm going to rewrite it as an argument where I'm saying if Q, then R. Now, the assumption with proof by contradiction is that I'm going to assume that not of P is actually true. Okay, so I'm going to assume that not of P is actually true, which implies that actually not of Q then R. Okay, so what is this equal to? Well, this is as good as saying if Q then R is as good as saying not Q or R. I'm just removing the conditional statement and rewriting it as a disjunction of literal. This piece in green over here is completely equivalent to this piece over here in parentheses. Okay, so both of these are completely equivalent. Which now, if I take a negation and I take a negation inside, that will make it Q and not R. Okay, so by assuming that not P is true, let me just quickly create a truth table here. So if I create a truth table for let's say P, Q, and if I'm using Q and R, so let's just be consistent with our variables. So this is Q, R, if Q, then R, and what I need over here is Q and not R. So let's get not R first, and here is Q and not R. Okay, so my truth table 0, 0, 0, 1, 1, 0, 1, 1. This makes it true for the following cases. Not R becomes 1, 0, 1, 0. Q and not R. Well, Q and not R in this case is 0, 0, 0, and 1. Okay, and so this is 0 and 1 is 0, 0 and 0 is 0, 1, 1, and 1 over here makes it 1, and then Q and not R, 1 and 0 makes it 0. Okay. All right. So given this truth table, one thing that I can immediately see in this case is that that by assuming in this case that not P must actually be true, which is saying this entire piece must be true, or by saying that this entire piece over here must be true. Q and not R happens to be true only in this case here. Okay, so by assuming that not P is true, I'm trying to find out, can I ever get this row here? Okay, this row over here, and more importantly, in this row, we're looking at this piece over here, and we're looking at this piece over here. Okay, so if I can never ever get Q equals to 1 and not R equals to 1, meaning I cannot ever get Q equals to 1 and R equals to 0. If this can never ever happen, well, if this can never ever happen, then not P, my assumption of not P actually being 1 can never ever happen, meaning this piece must always be 0. If not P is 0, that would imply, that would give you the kind of the idea that P then must be 1. Well, if P then is 1, if P then must be 1, P is actually 1 in the following cases. P is actually 1, happens to be over here. It happens to be 1 over here, and happens to be 1 over here, right? P is a statement, if Q then R. If P is that statement of if Q then R, it happens to be true only in these 3 cases, then you know that the original statement over here, P must be true, because not P can never ever happen. Okay, in the next video we're just going to look at this again, this kind of the high level idea, and see it using one form of truth table.